Unicast, broadcast, and multicast. Well, we're focusing on multicast. Find out why next, right here on IT Pro TV.
You're watching IT Pro TV.
That's right. We don't need no stinking broadcast because we have multicast. And here to tell us why, Anthony Sequeira. All right, Anthony. It's kind of one of these things as you start in your IT career, you start learning about unicast, which seems fine and normal, a broadcast, and then you hear about this multicast and you go, oh, it's actually just one to a group, and you're now starting to scratch your head a little bit more. But there is a reason why the world is advancing toward multicast. So help us out here and talk about the concepts that we'll be taking a look at.
Yeah, I love your intro there because I'm sure some of our viewers might not have made this realization yet, and that is broadcast in the IPv6 world is dead. Yay, finally. There is no longer the concept of a broadcast. By the way, the original idea for broadcasting wasn't that bad an idea. Think about it. You want to be more efficient than sending a copy of a packet to a whole bunch of systems. So the broadcast concept was initially a great one. We need an efficient way to send a single packet to everybody out there on the network. The issue is notice my little sketch here. There's two systems that want their IT Pro TV. I want my Dire Straits.
Dire Straits.
I want my MTV.
I get it.
I want my IT Pro TV. There's two systems that want to receive this information. And there is one system that definitely does it. They're busy watching The Mandalorian. So the issue if we use broadcast is what?
All of them will get it.
That third system gets it. Yeah, it doesn't want to, but it gets that packet. So multicast gives us this great paradigm where the two systems that want the information can subscribe to it. And it is very much like a television or cable type of an analogy, and that's why that analogy is often used. Something else that's interesting about the analogy is multicast is a great way to do audio and video type data, so it also holds up that way too. So multicasting is such a clever way to go, such an efficient way to go, that it does replace broadcasting, completely eliminates it in IPv6. In IPv4, it's just an enhancement. We still have broadcasting, of course, in IPv4 networks. But did you ever think about this question? In IPv6, if there's no broadcasting, what do we do when we have a packet that needs to go out to everyone? Well, they just created an all nodes multicast group, and that essentially is the replacement for the broadcast feature. So you still have a way selectively to get a packet to everyone in the area. So that's a great thing, or I should say segment to be more precise. So wonderful. Multicast. And what's interesting about the Encore presentation here is that they don't have us teach you multicast addressing. That's kind of assumed knowledge, I guess. Just remember that piece. I feel irresponsible, presenting this without reminding you that there's that Class D address range, and it is used for multicasting, and the participation in the multicast address space is how you're going to be joining the group. And we'll see at the end of this presentation today how there's the Internet Group Management Protocol, IGMP, is the protocol that's going to allow these stations to say, hey, look, it's official. I want to join the multicast group that is known by this particular IP address.
Now, according to your diagram, I'm seeing that router that's right there. Does that mean that multicast can go across boundaries, whereas normally broadcast are separated by the
yes,
router?
That's another great thing here is we're going to have a multicast type of protocol to forward this through the infrastructure. It's going to go and work through our switches and routers.
Nice.
and we're going to be able to multicast. Now, one of the things you can do, Ronnie, is scope it. And the addresses are set up that way where you have a range of addresses that is to be used in your private organization for multicast addressing. You have the glop addresses, great word. The glop addresses are for a different scope, and you can, just scope via the address space. Really interesting. And another interesting thing is not much changes when you get to IPv6. There's multicast reserved address space in v6, just like there is in v4. So you can very quickly learn the v6 multicast environment as you make the switch. So here we see that we've got just the machines that want to receive the information getting the information. That is the end goal of our multicast. Now, the first thing that I want to share with you about this is there needs to be some different loop prevention mechanisms than we have with our traditional forwarding of traffic in the traditional unicast forwarding environment. The first thing I need to impress upon you is that multicast works upside down from what we're used to. Let me explain. When we think about our routers and routing protocols for unicast, we always think of someone sending information that is trying to get to a specific destination, right? We think of, the router getting the packet and going, oh, where does this need to go? And then forwarding it to another device. And that device goes, where does this need to go? So it's a paradigm of moving traffic to a destination. Wrap your head around this. Multicast is the opposite. It's about taking traffic and radiating it away from a source. So it is a very different paradigm. It's a source sending out multicast streams, and we are concentrating on moving away from that source, not towards a destination. So that kind of leads me to this protection mechanism that's inside of multicast, and it's called the reverse path forwarding check, the RPF check, and it's super simple, Ronnie. Over on the left, I've got that cute little server of multicast content, right? It is sending out multicast, and the receiver is the little PC on the right. It wants to get the multicast feed. If we didn't have any kind of reverse path forwarding check, this is what would happen. The first router gets that feed and it sends it out its 2 links. The middle 2 routers get it. They send it out each of their links, and that final router gets it, that last hop router, we call it in multicast, an LHR. It gets it and sends 2 copies to the receiver out there. Not good. I mean, one of the reasons we wanted to multicast was we wanted to keep things totally efficient. And that would mean giving exactly 1 copy of the multicast information to that system. So this is one of the many times the RPF check kicks in and solves things for us. And it's automatic. We don't need to do anything.
Nice.
What happens is when that router gets those 2 copies, that last hop router, it looks in its unicast routing table. Okay, let's say it's OSPF that it's using for unicast. It looks in that table and it says, how would I get to the source? And that's going to be out one of its interfaces, the best path to get back to the source, right? It then accepts that packet and it drops the other packet that came from the other path. So isn't that interesting that multicast will rely on the unicast information for what's the best path to the source, and that's how it can do loop prevention, and in this case, preventing a duplicate transmission to the receiving system.
Now, since you used OSPF in this example, is there any special configuration in OSPF that we would need to
What a great question. So here's the great news. when they first were designing multicast, they did MOSPF, multicast OSPF. They were designing an OSPF version called MOSPF, thus my MOSPF joke. They were designing a special OSPF to be able to work with this. And then they realized, oh my gosh, we're going to have to design a special RIP, a special EIGRP. And they invented Protocol Independent Multicast, PIM. And the great news is protocol independent means it's going to work right out of the box with any underlying routing that you're doing. Static, dynamic, OSPF dynamic, RIP, it doesn't care. It is protocol independent as far as your routing protocols go. So now that we understand the RPF check, and notice, I forgot I had a little animation. The RPF check, remember, centers around that device saying, okay, how would I get to the source? And that's the only traffic that I'm going to accept as that loop prevention mechanism. So the first technology that was created around protocol independent multicast assumed that there would be a dense distribution of devices that want to get the multicast feed. It's called Protocol Independent Multicast Dense Mode, PIM-DM. It is, dense here is referring to a dense population of receivers. So how does it work? Well, think about it. If there's supposed to be this whole dense, everybody in the organization wants the feed, it floods it. It just sends it everywhere. And that's obviously going to be inefficient for your little areas like the Miami router in the top right. The Miami router doesn't have anyone out in its segments that want the multicast feed. So it's so silly that it keeps getting the multicast. So what does it do? It prunes itself off of the multicast distribution tree. We use the tree paradigm here, like in spanning tree and like in OSPF. There's this tree that's built. So, interesting. Flooding and pruning. And guess what has to happen? That pruning information has to kind of time out to make sure that, everyone that really does want it can get it. So you have a reflooding and then a repruning. And then there has to be a way for the Miami router to say, oh, wait, I do need the multicast. So it does a graft. Notice that prune and graft are like Arbor Day things, like trees and plants. So it's all a tree paradigm. When you prune a tree or graft something to a tree, super interesting. So PIM dense mode, it's not good. For a while, we were saying, oh, you would use this PIM dense mode if you did have a real dense distribution of people that wanted the feed. We no longer recommend this, ever. And I'll explain why in a minute. By the way, that technology is called a source distribution tree. Each source is going to be building this flooding tree, and it's just, that's how it works. Well, they quickly started looking at improved technology like the PIM sparse mode. The design here was, okay, for those environments that don't have a lot of people that want to receive it, let's use a shared distribution tree approach. This doesn't operate on the whole flood and prune paradigm. This operates on more of an explicit join. Hey, I want the feed. I want the feed. I want the feed. And they have a shared tree approach because they invented a concept called the rendezvous point. Sounds very romantic.
It does.
The rendezvous point, or RP, is a centralized location that the multicast can be sent to that others can get the multicast from. So notice in this situation, the rendezvous point becomes the Miami router. The Miami router is now getting the multicast feed. Notice a client off the Orlando router sends what's called a star comma G. The star is a wildcard. The G is saying for any group, I want to, receive multicast from you. So it's going to the rendezvous point and saying, look, send me the multicast feed for any sources. Okay? So the rendezvous point goes, okay, no problem. I'm the rendezvous point. I'm getting the multicast and I'll send it down to you. Now you notice a problem here. The multicast traffic, Ronnie, is going from Tampa to Miami to Orlando under this paradigm. That doesn't seem very good because it would be much more efficient to go Tampa to Orlando. So they invented a fix for that. It's called the shortest path tree switchover, or SPT switchover. And this topology realizes it's inefficient. There's mechanisms inside to realize the inefficiency. And the Orlando goes, wait a minute, I'm going to send a source group entry, not a wildcard group entry, but a source G entry, SG entry, right to the Tampa router. And it says, you know what? For that source, just give it to me directly. And now, just seamlessly, the inefficient rendezvous point is no longer used. What these mechanisms bring together for us is a situation, Ronnie, where the PIM sparse mode becomes the ideal technology for any topology.
Right.
We don't see PIM dense mode being used anymore, even in topologies where you have a dense distribution of receivers, because PIM sparse mode is engineered to be great for any type of distribution.
All right. So with the Miami router at this point, does this, the way that we have the rendezvous point, does that Miami router have to have, let's say, a multicast group off of it that it's receiving for?
It doesn't.
It doesn't.
The rendezvous point is set in the network.
Oh, okay.
And it's going to receive the multicast feed because it is essentially the root of the tree, if you want to look at it that way. Yeah. Now, Ronnie, the rendezvous point.
Right.
How would we set that? Well, there is 3 technologies or 3 methods of setting it. Super interesting. A lot of people statically set it. So they go to all of their routers that need multicast and they say, your rendezvous point is at 3333. You can statically set the RP. Cisco has a proprietary method for automatically setting it, called Auto RP. And there is the funniest chicken and the egg problem with that technology. It uses multicast in its operation. So you get this chicken and the egg situation because, wait a minute, if you need multicast to set the RP, what's the RP for the auto RP?
Right.
And, they solve that, but it's just hysterical that there's challenges like that with auto RP. There is an open standard way to set it dynamically, and that's, I think, very popular. I don't see auto RP implemented nearly like I see BSR. That's called Bootstrap Router Protocol, and BSR is the open standard way to automatically set the rendezvous point. So this is a video you're going to want to watch a few times if you have never encountered multicast. I should have made that clear. So if you have never encountered multicast and you feel like your brain is melting right now, have no fear. Watch this video several times. So the last thing that we have to talk about here, we know that we love PIM sparse mode, that it's ideal for all of our topologies. And one more note on that, there is some variations for specific scenarios, like there's something called bidirectional PIM. And there are some other variations, but I really want you to know the whole PIM sparse mode versus dense mode thing. But we need to wrap this up with a discussion of how do those systems notify the network that they want their MTV, IT Pro TV. How do they make that notification? Well, there's the Internet Group Management Protocol. You know that I struggle with acronyms, but I'll never forget that one. And that's because most people mistakenly call it the Internet Group Multicast Protocol, but that is not its name. It's the Management Protocol. And there's been 3 versions throughout the years. Each version offers remarkable improvements over the previous, but the most commonly used version is version 2. Version 3 added some source-specific multicast kind of fun stuff where a device can say, I want this multicast, but I want it specifically from that server over there. That's not often needed, so version 2 is what you see implemented a lot. The device with IGMP tells the local router, I want multicast traffic for this group. It's a key piece of this puzzle. Similar technology exists in the version 6 of this, the IPv6 version. But it's really interesting because I haven't shown you a realistic topology. There would be a switch that the device is connected to that wants the feed. And for the longest time, this was problematic. There was the CGMP protocol. And CGMP was a Cisco invention that allowed switches to talk to routers about the IGMP information. So the router would essentially say to the switch, hey, Mr. Switch, don't flood the multicast everywhere. Just send it out that one port. And that was a problematic thing because it should be easier than that for the switch to process and understand IGMP. So the end solution, IGMP snooping. The switch eavesdrops on the IGMP messages and then realizes what ports it needs to forward the multicast traffic out of. A very simple solution. You're almost like, why didn't they invent that right away? I think one of the reasons is they needed the new ASICs and stuff to be able to do those determinations in hardware and not really slow down the switch. So Ronnie, there is a look at the topics that we need to be responsible for at the Encore level. Note, it is conceptual information only, not configuration information. It is really relegated to what multicast is, the RPF check, PIM dense mode, PIM sparse mode, our rendezvous point concept and the 3 ways to set it, and the glorious IGMP protocol.
All right, Anthony. Well, thank you for helping us there in terms of making sure that we know those concepts. Make sure you go back and take his advice to review again, but he gave us a nice wrap up there. So this is a great place for us to go ahead and end this episode then. Signing off for IT Pro TV, I'm your host, Ronnie Wong.
And I'm Anthony Sequeira.
Stay tuned right here for more of your CCNP Encore show.
Thank you for watching IT Pro TV.